All right, let's have a look at question 9 on mass balances. And this question, is taken from a tutorial. So it looks like quite a bit of text. So let's go through it. All right. They say to me, humid air, which is air which contains water in the vapor phase, must be dried before being used in a process plant. So you can imagine if I needed to send air, let's say, into a piece of instrumentation. So you know that a valve, which is basically like an open-close switch or an open-close mechanism for a pipe, if you needed to close that valve, sometimes they are pneumatically supplied, which means you need to supply air into that valve to close it. But if you keep sending water into your valve to close it, eventually that's going to cause some damage, right? So you want to make sure that you only send dry air into your valve. So let's say that's where we are sending the air to, okay? The wet air is fed into an adsorber. So I always wondered, why are people spelling the word absorption wrong? And then I realized, no, adsorption is actually a thing. So think about it like this, right? And this is not important to the question, but it's just nice if you know it. So here's a man standing, and here's a pie, right? A nice chicken pie. If he ingests that pie, that is absorption. I saw this picture on the internet once, and it really stuck with me. That's absorption, right? Because it enters his body and digests it. But let's say here's a man standing, right? This guy looks like a wrench from Handy Manny, okay? And here's a pie, okay? But I throw it at his face. That is adsorption. So adsorption basically means that something sticks to your face, and absorption means that you ingest it. Okay, so that's the difference between absorption and adsorption. If it's absorption, it's going to become a part of the molecule. It's going to become, absorbed by the molecule. And if it's adsorption, it's just going to stick to the outer edges of the molecule. All right. Let's continue. So the wet air is fed into an adsorber at 2.3 cubes a minute. It contains 1.5% water. Remember, the water is as a vapor. So this is on a mole basis. Remember, anytime someone gives you the composition of a gas, and if you've watched any of the ideal gas questions, you'll remember me saying this. If someone gives you the composition of a gas, you always assume it's on a mole basis. Okay, the wet air flows into this adsorber, and they give me the pressure, and they give me the temperature. You'll remember I told you in the ideal gas section, if someone gives you a gas composition and they give you a pressure and a temperature, you already know that you need to use the ideal gas law. Okay, the adsorber is basically a tank with 30 kgs of aluminium trioxide or alumina pellets. The water vapor in the adsorber sticks onto these pellets. So what's happening is we've got a nice tank here, and it's filled with little pellets or balls of alumina catalyst. All right. And what's happening is my wet air comes in. Okay. So that's air plus water. Okay. The water gets stuck onto the edges of this alumina. So these red balls are little water molecules, right? The water molecules get stuck onto the edge of my catalyst, and out comes dry air. Okay. That's just so you can visualize what's happening. And in here, we've got 30 kilograms of these alumina balls. All right. The water vapor in the air adsorb, okay, it sticks onto these pellets, and the air that exits contains very little water, 0.06%. The alumina can adsorb 0.2 kgs of water for every 1 kg of alumina. 1 kg of alumina, 200 grams of water, before it needs to be replaced by a fresh batch. So question A says to me, what is the mass flow rate of water into the tank? You'll remember anytime we start a mass balance question, what's the first thing they ask us to do? Draw the picture. Okay, so this is going to be my adsorber tank. Wow, these lines are so skew, I'm ashamed. Let me just neaten this up a bit. There we go. Okay, so into the adsorber, I'm going to call this stream, and it's always useful to name your streams. Okay, so into the adsorber, we've got WA. I'm calling that wet air. Exiting the adsorber, we've got DA. I'm calling that dry air. And out of the adsorber, I have water exiting, but I'm going to call this the evap stream. Okay, so that's my, no, not evaporation stream, sorry. This is not a heater, this is an adsorber. So I'm going to call this the adsorption stream. Okay, so we've got wet air coming in, adsorbed water attaching to the catalyst in the tank, and dry air exiting. All right, I know that we've got 2.83 cubes a minute of wet air. Let's write that down. I've got 2.83 cubes per minute of wet air. Okay, that's fine. And I know that it contains 1.5% water. So remember, that's 1.5 mole percent H2O. And so, of course, it's got 98.5 mole percent of basically air. Okay, so remember, if it's not water, it has to be air, right? And I also know what the pressure is. It's 111.5 kPa. So P equals 111.5 kilopascal absolute. The absolute is just to tell you that it's not a gauge pressure. If it was a gauge pressure, then we would need to add on the atmospheric pressure. Okay, but you always use absolute pressures in your ideal gas law. And they also told me the temperature is 28.3. Quickly, before the Kelvin police find you, convert that into Kelvin. So 273 add on 28 is 301.3 Kelvin. Okay, now we can breathe. The Kelvin police are not out to get us. Then we've got the dry air, and thank you to my lecturer for teaching me that. I learned that from her. Now, we've got a dry air stream. The only thing I know about the dry air stream is that it contains it was very dry, remember? 0.06% water. So I know that the mole percentage of water is, mole percentage water equals 0.06%. Okay, and then of course the remaining 99.54% is going to equal to air. Okay, and then in the adsorption stream, remember that's obviously going to contain 100% water, because these alumina particles are only adsorbing water, nothing else. Okay, so we're off to a good start. And the first question says to me, what is the mass flow rate of water in the tank in kilograms per minute? So let's see. I've got this wet air in volume. So I know volume, I know pressure, and I know temperature. So I can apply the ideal gas law. Let's go for it. So part A, I know that PV equals number of moles times R times T. My pressure, 111.5 kPa. My volume was 2.83 cubes a minute. And I'm going to turn this into put dots on top. What does the dot represent? It represents a flow rate per unit time. Okay, 2.83. Number of moles, I don't know. All right. R stays constant at 8.3145 if you're using the correct unit system. And then your temperature was 301.3 Kelvin. All right. And if you calculate all of this, you get the number of moles. And this is the number of moles of total wet air. Okay, so this is the total number of moles in your wet air stream. And that's going to come out to be 0.126. 0.126 kilomoles of wet air per minute entering the stream. Okay, but I didn't want number of moles, right? The question asked me for the mass flow rate. So how do I convert from moles into mass? You can say it with me. You use the molar mass. So how do we calculate the molar mass of our wet air mixture? Well, if you remember, if you've got a mixture from ideal gases, then the molar mass is equal to the mole fraction of component 1 times the molar mass of component 1 times the mole fraction of component 2 multiplied by the molar mass of component 2. Okay, so my wet air composition, remember, was 1.5 mole percent water. So this is 1.5% water, and the molar mass of water is 18, plus 98.5% air, and the molar mass of air, if you need to work this out, you can, and I'll tell you quickly. Remember that air is 79 mole percent nitrogen, 21 mole percent oxygen. And so if you do the same formula here, 79% of 28 plus 21% of 32, that should give you an average molar mass of 29 kilograms per kilomole. That is how you calculate the density, not the density, but the molar mass of air. Okay, so the molar mass of air is 29 kilograms per kilomole. So the molar mass of the wet air comes out to be 28.835 kilograms per kilomole. So what I'm going to do is, remember, I always like to keep my thoughts structured, right? So I'm going to put the ideal gas law in a box, and then I'm going to put the molar mass calculation in another box, and then I'm going to do my conversion in yet another box. So I know that the mass of wet air, and you can put a dot on top if you want to, is equal to the number of moles of wet air in that stream multiplied by the molar mass of wet air. So that is going to equal to, my number of moles was 0.126. So 0.126 multiplied by 28.835. And that's going to come out to be, that's 3.63. Oops, sorry. Sometimes, I think that I write things down, but I don't. So 3.63 kilograms of wet air. So that's my total mass flow rate of wet air. But now I see, if I go back to the question, it asked me, what is the mass flow rate, not of wet air, but of water into the tank in kilograms per minute. So I apologize. I didn't make a mistake, but that's not what the question is asking. They want to know how much water is in the air. So I'm going to start from here. I know the number of moles of wet air, right? And let's write this down. But it's okay. We just did a little bit of extra calculations. The number of moles of wet air is 0.126 kilomoles of wet air. But I know that if we go back up here, the amount of water in the wet air is 1.5 mole percent. So I know that 1.5% of all the moles in here is equal to the water moles. So the number of moles of water in the wet air stream is equal to 1.5% of all the moles in the wet air stream. So that's 1.5% of 0.126. And now my book makes a bit more sense. And it says to me, I have 1.89 times 10 to the minus 3 kilomoles of wet air. And this is per minute. And this is also kilomoles of wet air per minute. Okay. But the question didn't ask me how many moles of water you have in the wet air. It asked me, what is the mass of water in the wet air stream? So that is equal to the number of moles of water in the wet air stream multiplied by the molar mass of water. So that is 1.89 times 10 to the minus 3 multiplied by 18 kilograms per kilomole. And that comes out to be 0.034 kilograms of water per minute. Wow. Okay. That was a long question, but I made it more difficult than it needed to be. But it's fine. We learn every day, right? So now I know the mass of water in the wet air, and that is 0.034 kilograms. So I can actually go up and write it here if you want to. 0.034 kilograms of water. And remember the stream's total mass was, which I unnecessarily calculated, but the stream's total mass was 3.63 kilograms of water, of wet air, So this is 3.63 kilograms of wet air. So remember, 3.63 kilograms is wet air. Only a small amount is water. So if I subtract these two, I will know how much air is in the wet air stream. Okay, let's proceed. B says to me, what is the mass flow rate of water out of the tank? So here we're getting into the real mass balance stuff. Do you agree with me? If I know the total mass of water coming in, right, and I can work out the total mass of water coming out, then the only unknown is the mass of water in the adsorption stream, right? So, sorry, that will be called a component mass balance, because I'm taking the amount of water entering, and that is equal to the amount of water in the adsorption stream plus the amount of water in the dry air stream. So we're going to do a component mass balance for the water. Okay, so let's do that. Part B. I know that the mass flow rate of water in the wet air stream must equal to the mass flow rate of water in the evaporation stream, in the adsorption stream, plus the mass of water in the dry air stream. Okay, so I know the mass of water in the wet air stream, right? We just worked it out. It was 0.034 kilograms of water per minute. But I don't know how much water is in the dry air stream, and I want to work out the mass of water that is being evaporated, right? Or let me just see that again. What does the question ask me? What is the mass flow rate of water out of the tank? So I actually want to know what is the mass flow rate of water here. Okay, and I want to know what is the mass flow of water in the adsorption stream. So now, and I didn't make a note of this, but this is a component mass balance for H2O. Okay, so now we're just going to sit and think a little bit, right? What is the mass of water in the adsorption stream? We don't know. And we want to know what is the mass of water in the dry air stream. Fortunately, they did give me some information. They told me that the mass of water in the dry air stream all over the total mass of the dry air stream must equal to 0.06 0.06%. Oh, wait, is that 0.06%? Okay, the air that exits the tank contains 0.06%. That's a mole percentage. So I apologize. Rookie mistake. This is going to be number of moles of water. And this is going to be number of moles of dry air. Okay. A number of moles in the dry air stream. So where do we go from here? We want to know how many moles are in the dry air stream. So I can expand this a bit. This becomes the number of moles of water in the dry air stream all over the number of moles of air in the dry air stream plus the number of moles of water in the dry air stream. Because you agree, the dry air stream is made up of water and air, and that is still equal to 0.06 mole percent. Okay, so do you agree the number of moles of water in the dry air stream is unknown, and this is also unknown, right? So this is one variable. So what I can work out is the number of moles of air in the dry air stream. So how many moles of air did we have in the dry air stream? Let's see. Okay, I hope you're following me. There's a lot of words going around. Okay, So remember I said to you that I can tell you how many moles of air I have in this stream, right? In the wet air stream. All of the air in the wet air stream must exit out of the dry air stream. So I know that there's also air exiting this stream, right? And the air that exits here must equal to the air that's entering here. So can you work out how many moles of air is coming into the wet air stream? That's very easy. It's 98.5% of my total air coming in. Okay. So I know that I'll write down the component mass balance for dry air. No, not for dry air. Component mass balance for air. Okay. So what that says to you is the number of moles of air in the wet air stream must equal to the number of moles of air in the dry air stream. And you agree with that, right? I don't see any flaw in that logic. Now, how many moles of air are in the wet air stream? Well, I know that 98.5% of all the moles in the wet air stream. Let's write that a bit neater. 98.5% of all the moles in the wet air stream must equal to the number of moles of air in the dry air stream. So, number of moles of air in the dry air stream is equal to 98.5% of 0.126. 98.5% of 0.126 is 0.124 kilomoles per minute. Okay, so I'm going to put this in a box just to keep my thoughts organized. And you can see things are getting not hairy, but you've got to be very diligent in your calculations. So I know that this is 0.124. So now I can solve this equation using my programmable calculator. 0.124 plus x is equal to 0.06%. Now I'm going to solve for x. Okay, that's 7.44 times 10 to the minus 5. Wow. Okay, 7.44 times 10 to the minus 5. So where can I write this now? Okay, let's just continue this down here. And I'm going to say, therefore, the number of moles of water in the dry air stream is equal to 7.44 times 10 to the minus 5 kilomoles per minute. Okay, that's how much water is in the dry air. So it's a very, very small amount. But did the question ask me to find how much water is in the dry air stream? Yes, but they asked me to find how much water in mass flow is in the dry air stream. So now I've got to convert this number of moles right here into a molar mass. So as my final step, I know that the mass of water in the dry air stream is equal to the number of moles of water in the dry air stream multiplied by the molar mass of water. So that is going to equal to 7.44 times 10 to the minus 5 multiplied by 18. And that gives me 1.34 times 10 to the minus 3 kilomoles of water, not kilomoles, kilograms of water per minute. Okay, and that is the answer to part B. Okay, so now that I've got this, once you get these numbers, right, it's very difficult to keep them in the back of your mind and to focus on the next question because it's all occupying bandwidth. So I'm going to write down what I've just discovered on the picture. 1.34 times 10 to the minus 3. So water, 1.34 times 10 to the minus 3 kilograms per minute. The airflow rate is equal to the number of moles that I calculated previously. How much air is in this mixture? We worked it out here. it was 0.124 kilomoles per minute. So 0.124 kilomoles per minute. Okay, so now I know how much air and how much water is in the dry air stream. And I also know how much water is in the dry air stream. And then I can also work out how much air is in the wet air stream. It's 3.63 minus 0.034. Okay. So actually, let me just do this calculation here. 3.63 minus 0.034, 3.596. So you can see 3.596 kilograms of air. You can see that air really does make up most of the stream. 3.596 kilograms comes from air. A few, 34 grams comes from water, and that gives you a combined mass of 3.63. Okay, I know what my dry air composition is, and then to work out the mass of water adsorbed is very easy as well. Now they ask me for part C, how long can the tank be operated before the alumina needs to be replaced? So I basically want to know how much water is the alumina adsorbing. So that's a good place to start. So you remember I wrote down my equation earlier, this one, right? Mass of water in the adsorber, mass of water in the dry air. So let's write down that component mass balance again. So this is the component mass balance on water. And it basically says to you that the mass of water in the wet air must equal to the mass of water in the adsorption stream plus the mass of water in the dry air stream. So how much water was in the wet air stream? We can go up and check that out. We worked it out here. Mass of water in the wet air stream, 0.034. Okay, so that's 0.034 kilograms per minute. We don't know how much water is in the adsorber. And then the mass of water in the dry air stream, I also worked out. Mass of water in the dry air stream was 1.34 times 10 to the minus 3. 1.34 times 10 to the minus 3 kilograms per minute. And so the mass of water in the adsorption stream must equal to 0.0327 kilograms per minute. So I'm going to put that answer in a box because that's good. And I'm going to need this piece of information a bit later. So I know how much water is now in the adsorption stream. That's very good. But remember, if we go up a little bit further, we want to know how well does the catalyst work. So they told me the alumina can adsorb 0.2 kilograms of water for every 1 kg of alumina. And I've got 30 kgs of alumina in the tank. So let's go down and do that ratio conversion, right? They told me 0.2 kilograms of H2O is adsorbed, okay, for every 1 kg of Al2O3. But I don't have 1 kg of Al2O3. I've got, I can't remember that number, 30. Okay, I've got 30 kilograms of Al2O3. And so in total, I should be able to absorb 6 kilograms of water per batch of alumina in the tank. Okay, so I can absorb 6 kilograms of water. That's good, but remember, I am adsorbing water at a rate of 0.0327, right? So 0.0327 kilograms of water adsorbed every single minute. Okay? And my one batch of alumina is doing 6 kilograms of water. Okay? So in 1 minute, I'm absorbing 0.0327. Let's just simplify that. That's 32 grams. Okay? So in 1 minute, I'm doing 32 grams. How long will it take me to get to 6 kilograms? Okay. So actually, okay, it's fine. Let's keep going. You'll see what I'm going to do now. 0.0327 divided by 6. That's 5.45 times 10 to the minus 3. And if you look at my units, this is where I made a hiccup. The unit is 1 over minute, right? Because the unit is in the denominator. So that's 1 over minute. So that does not make a lot of sense to anyone on the planet. So I'm just going to invert that number. And I get 183.49 minutes. So that is how long it takes for all the alumina in the reactor to adsorb as much water as it can. So after 183 minutes or 3 hours, I'm going to need to change over the amount of alumina in the reactor. Okay, so I think that's it. Good, great stuff. 183 minutes. Now, let's get on to the last question, part D. So part D says to you, the porosity of the bed of alumina in the tank is epsilon equals 0.42. We're going to talk about this just now, okay? The density of alumina is 3,970 kilograms per cubic meter. If the packed pellets are completely filling the tank, specify the tank's volume. So the first step in solving any problem is making sure you're solving the right problem and understanding the problem. So let's have a look at this, right? Let's define porosity first. Okay, and then I'm going to need to draw a few pictures just to make sure that you understand it. So generally, when we deal with porosity, that's dealing with reactor catalysts, and you'll deal with more of that in closer to your final year when you do reactor design. So epsilon equals 0.42. The porosity is defined as the volume of empty space divided by the total volume occupied. Okay, so 0.42 is equal to the volume of empty space divided by the volume of empty space plus the volume of solid particle. So what does this mean, right? I want you to picture, let me just put this in a box so it looks a bit neater. I want you to picture a little ball of alumina catalyst, right? Inside of that alumina catalyst, it's got these tiny little channels, right? Within this ball, tiny channels, okay? You probably can't even see it with your eye, but it's these tiny channels. And so let's say the total volume of this, right? If I calculated the volume of a sphere, I think that's 4 over 3 pi r cubed or something like that. And let's say I calculated the volume of the sphere and it came out to be 1 cubic meter. That is the total volume occupied. But the volume occupied by air is going to be 0.42 or 42% of that 1 cubic meter. And the volume of actual solid alumina, that is going to be 1 minus 42 or 58% of the 1 cubic meter. And this is 0.42 cubic meters and 0.58 cubic meters. I think this is the best way to explain it. So can you see how I'm occupying a total volume of 1 cubic meter? But of that volume, a lot of it is just air spaces. That is defined as the porosity. And then the inverse of porosity, or 1 minus the porosity, there is a term for it, but I cannot remember what it is. And that will be the volume occupied by your solid. So keeping this in mind now, right? I want you to keep this picture in mind. Let's try and solve this problem. So they said to me, I've got a tank, right? Off to a shaky start, hey? All right. And here's my alumina pellets. Okay. And it's all nicely stacked up. Okay. But in these alumina pellets, I've got all of these channels that only contain air. There is no catalyst in these channels. Okay. And I know already that the mass of all of this catalyst, and remember the container is filled, right? So I'm just going to add one more alumina particle in here. Okay. So I know if I put this on a scale, right, the total mass of all of this alumina was equal to 30 kilograms. Yes. Okay. 30 kilograms. All right, that's good. Now, remember, this volume of this container is X, some unknown amount. But I know if I put this thing through a hydraulic press, right? I absolutely compressed all of my catalyst such that there are no air spaces anymore, right? So here's my container, and I hydraulic pressed everything so that my alumina catalyst is now sitting here, okay? And it's a completely solid compound. So I guess because it's solid, it shouldn't have any stripes in it. It should be completely colored in. All right, so this is completely solid alumina catalyst now. There is no space for any kind of air. If I compressed all of that down, do you agree it's still going to weigh 30 kgs, right? But what volume does it occupy? Well, the volume, okay, all right, fine. We've got 30 kgs here. What volume does it occupy if you've compressed it? Well, I know the density of alumina. The density of alumina was, let me get it from here, 3970 kilograms per cubic meter. Okay, so you can do a quick conversion here. So the volume occupied by solid catalyst particles is equal to 30 kilograms. Okay, let's do this the other way around. I know that 1 cubic meter weighs 3970 kilograms, but I've only got 30 kilograms. So the volume occupied by the solid is going to equal to 7.56 liters. Okay, so I just multiplied that by 1,000 to get liters. So I know that 7.56 liters is actual solid volume. But I know that 42%, right? 42% of all the volume occupied. Okay, sorry. Let's restart that. 58% of all the volume occupied is equal to 7.56 liters. And then you can say, therefore, 100% of all the volume occupied is equal to some unknown amount, which you can solve for. But doing it like this is intuitive, which is okay. You can solve it like this. So you can say, all right, what's 7.56 divided by 58%? And then times 100%, right? Which is 13.03 liters. Okay, but that's fine. And if you're happy with that, that's okay. But let's try and use the equation that we have here, because I think this is a good way to express it, right? 0.42 is equal to the volume of empty space over the volume of empty space plus the volume of solid. So I want to use that equation, okay? So I know that 0.42 is equal to the volume of empty space, and you know what I mean by empty space, right? Empty space means it's not filled by a solid, it's filled by air, over volume of empty space plus the volume of solid catalyst particle. So I said that the solid catalyst particle I know as 7.56 liters. So 7.56 liters is actually being occupied by solid alumina particles. So the rest of this must be empty space. And if I solve this in my programmable calculator, then I get that the volume of empty space is equal to, oh, and I didn't work it out. Okay, so let's do that, right? 0.42 is equal to an unknown amount over an unknown amount plus 7.56. And if we solve for this, we should get that the volume of empty space is 5.47 liters. Okay, but the volume of my tank needs to equal to the volume of solid particles plus the volume of empty space. And that's going to equal to 7.56 liters plus 5.47 liters to give me 13.03 liters. That is the volume of the tank. So as always, present your answer with pride, make it look nice, and keep all your steps in a very logical sequence. So I hope this makes sense. I tried my best to explain the porosity. If it's a bit confusing, just have another look at this video and hopefully things will start to come together. So thank you very much for watching. I appreciate your time. I hope this was helpful. And if there are any more questions, feel free to ask them in the chat box. Thank you and goodbye.